Let's talk about the theory behind acid-base chemistry. We're going to talk about two types of acid. The first is the Arrhenius acid, and then the modified Arrhenius acid theory. So in the original Arrhenius theory, which is the first theory often taught to students studying chemistry, and you may have studied this before in your other courses, in Arrhenius theory, acids just regularly ionize in water to produce hydrogen ions. So the example here is we have hydrochloric acid, HCl, ionizing, becoming hydrogen ions and chloride ions. Again, this is an ionization reaction. On the other hand, bases, they merely dissociate, they separate into the ions to produce OH, hydroxide compounds. So the OH here, if you remember, is a hydroxide ion. Right, so here we have sodium hydroxide dissociating a sodium ion and hydroxide ion. Let's look at some examples of Arrhenius acids. So here we have a series of acids. We have HBr, hydroborobic acid, HNO3, nitric acid, and so on. And all of these compounds have a hydrogen involved, right? Because remember, our definition of Arrhenius acid is that they ionize into hydrogen ions and some sort of cations. The exception here, or the different one here, is acetic acid, right? This is CH3COOH, also known as vinegar. Now in acetic acid, the H is placed last because it is associated with the acetate ion. Let's look at some examples of Arrhenius base. Now remember, Arrhenius base is a compound that dissociates into a cation and hydroxide ion. So here, in purple here, we've denoted all the cations, and in red are the hydroxide ions. Some compounds, such as sodium hydroxide and potassium hydroxide, will only give you one hydroxide ions, whereas compounds like barium hydroxide and strontium hydroxide will dissociate to give you 2 moles of hydroxide ion for every 1 mole of the base. We should also look at examples where a chemical compound, even though it appears to be a base, is not actually a base. The example here is methanol, CH3OH. We see that there's an OH here, and we automatically assume that because there's an OH, it will dissociate to give you hydroxide, and whatever the CH3 compound will become. However, you have to remember from your bonding work that the bond between the carbon and the oxygen in hydroxide is a covalent bond here, and the covalent bond is very strong, and it will not dissociate or ionize when placed into water. Therefore, covalent compound, molecular compounds, such as methanol, is not a base. So in the world of chemistry, the Arrhenius definition of acid and base is rather limited. There are examples, such as this one here, sodium dihydrogen phosphate, that does not have an apparent H to ionize, but if you test it with pH paper or litmus paper, you will discover that it is indeed an acidic solution. Why is that? Our original Arrhenius definition does not predict this to be an acidic compound, so we have to change our original assumptions into what is called a modified Arrhenius theory. So our original assumptions is not working. Our Arrhenius theory cannot explain why compounds such as sodium hydrogen phosphate create an acidic solution. But when we put sodium dihydrogen phosphate into water, it does dissociate into sodium ions and dihydrogen phosphate ion. None of this contains our original H plus ion that we would expect for a acidic compound, so how does the acid form? In order to account for the acidic properties of the solution, we have to talk about a new molecule, what is called the hydronium molecule. So what is this hydronium molecule? It is the molecule that accounts for the acidic property of a solution. So let's go back to dihydrogen phosphate for a minute, H2PO4. Right? It will react with water to produce our hydronium ion. So here we have a reaction. Dihydrogen phosphate reacts with the water, giving you H3O plus hydronium ion and monohydrogen phosphate. Now this reaction will happen with any ion that contains hydrogen to produce hydronium ion. Let's look at the hydronium ion some more. Hydronium ion, we said, is the product of something, an anion reacting with water. So if we look at the original Lewis structure of water, which you may have done in other courses, right, we see that we have a lone pair here from the water that is now going to be attached to one of the hydrogen to give you a hydrogen that is covalently bonded to the oxygen. So here's a Lewis structure, and here is the Vesper structure of the hydronium ion, and here is the molecular geometry. As you can see, it is going to be a trigonal pyramid shaped molecule. Remember, water was a bent molecule, but now with the addition of a hydrogen ion, it now becomes a trigonal pyramid shaped molecule. So that takes care of the acid, but bases also have problems. If we look at a solution such as ammonia, NH3, we don't see any obvious source of hydroxide. Right? Remember, OH minus is hydroxide. But yet, if we test a solution of ammonia with pH paper or litmus paper, we find that it's basic. Without any sort of obvious OH, how do the basic properties form? So, under our original Arrhenius model, we cannot explain why something like ammonia would have basic properties. So, we have to change our definition into a modified Arrhenius definition. So, in this case, a base is something that reacts with water to produce hydroxide ions. So, ammonia here will react with water, H2O, to produce hydroxide. And in order to properly balance this chemical equation, we have to take one of the H that was lost from water and add it to ammonia to make ammonium. And as previously mentioned, sometimes it's more beneficial to write water as HOH. In this case, you can clearly see that this H here has been transferred to ammonia to leave you with free hydroxide and the ammonium ion. Another benefit of the modified Arrhenius theory is now we can categorize bases and acids into strong base, weak base, and strong acid, weak acids. So before we said strong acids ionize 100%, right? Now we can say that they will react with water to form hydronium ion in a 100% forward reaction. All of the hydrochloric acid will react with water to produce hydronium. Similarly, we can define a strong base as something that will fully dissociate into its ions, hydroxide ion and its cations. So the example here is lithium hydroxide fully dissociating into lithium ion and hydroxide ion. Now, you do have to remember and memorize the 6 strong acids, and here they are. We have everyone's favorite, hydrochloric acid. Its friend, its cousin, just below it on the periodic table, is the hydrobromic acid, followed by hydroiodic acid. The other strong acids are perchloric acid, HClO4, nitric acid, HNO3, and H2SO4. Of note here is the acid hydrofluoric acid, HF. You would assume that being fluoride, being cousins to chloride, bromide, and iodine, HF would be a strong acid, but it is not. HF is actually only a weak acid. Similarly, there are 6 strong bases that you should be aware of. These are all bases with cations in the group 1a, alkali metals, and group 2a, alkali earth metals. So these are sodium hydroxide, potassium hydroxide, and lithium hydroxide. On the alkali earth metal side, we have barium hydroxide, strontium hydroxide, and calcium hydroxide. That should say CaOH2. So remember your 6 strong acids, your 6 strong bases. Everything else is a weak acid or a weak base. And in our next video, we'll talk about how we can show the production of those hydronium ions and hydroxide ions.